Welcome to the new era of video creation with Baoz8. This is our new series on AI teaching natural language processing. Today, we will discuss the text summarization. Here are the contents. Text summarization is a fundamental task in natural language processing, NLP, that involves generating a shorter version of a larger text while preserving its essential meaning. Summarization can be categorized into two primary approaches. Extractive summarization. This approach selects a subset of sentences, phrases, or words directly from the input text to form the summary. Abstractive summarization. This method involves generating new sentences that capture the main ideas of the original text, often using techniques like paraphrasing or rewriting. Summarization is crucial in many applications, such as news summarization, research paper summarization, chatbots, and content aggregation. Given the exponential growth of information, text summarization techniques help us digest large volumes of text efficiently. Summarization can be broadly categorized into extractive and abstractive methods, but there are also other important distinctions. Extractive summarization. In this approach, the model identifies key sentences or phrases in the original text and directly extracts them to form the summary. This method preserves the original wording but may not capture the core meaning as succinctly as possible. Abstractive summarization. Abstractive summarization is more complex as it involves generating new sentences that encapsulate the meaning of the original text. This method often requires sophisticated language models to paraphrase effectively. Single document summarization. Summarizing a single document to produce a brief summary of its content. Multi-document summarization. This involves synthesizing information from multiple documents to create a coherent summary, often used in situations where diverse sources need to be aggregated, like news articles on the same topic. Text summarization, especially abstractive summarization, presents several challenges. Coherence. A good summary needs to be coherent and easy to understand. The sentences in the summary should flow logically from one to the next, which can be difficult to achieve, particularly in abstractive methods. Information loss. A key challenge is ensuring that the summary captures the most important information from the original text. Extractive methods are less likely to suffer from this problem, but abstractive summarization often runs the risk of losing critical details. Ambiguity. Language can be ambiguous, and generating a summary that preserves meaning requires understanding subtle nuances and context. This is particularly difficult when dealing with complex or highly technical texts. Evaluation. Evaluating the quality of a summary, especially for abstractive methods, is non-trivial. Unlike extractive summaries, where a metric like RAUJ, recall-oriented understudy for gisting evaluation, can be used, abstractive summaries require more sophisticated evaluation metrics. Extractive summarization works by identifying and selecting the most relevant sentences or phrases directly from the original text. The key techniques used in extractive summarization include TF-IDF, term frequency inverse document frequency, a statistical method that weighs the importance of words based on their frequency in the document and across a set of documents. Higher weight words are more likely to be included in the summary. Text rank, a graph-based algorithm that ranks sentences by analyzing how frequently they are connected to other sentences based on shared keywords. It's inspired by Google's PageRank algorithm. Latent semantic analysis, LSA, a technique that uses singular value decomposition to capture the underlying structure of the document and identify key sentences based on their semantic similarity. These methods are relatively straightforward and often produce coherent results, but they may lack the ability to generate concise and grammatically fluid summaries. Abstractive summarization is more complex because it generates new, coherent sentences that summarize the content of the original text. Rather than simply extracting existing sentences, abstractive methods attempt to paraphrase and condense the information into a more concise form. Common methods for abstractive summarization include sequence to sequence ASIQ2CQ models, which are typically based on recurrent neural networks, RNNs, or long short-term memory, LSTM networks, and more recent approaches like transformer models, e.g., BERT or GPT. These models require a deeper understanding of the text, as they must identify the key ideas, condense them, and generate new sentences that maintain the meaning of the original text. Abstractive summarization often results in fluent, concise summaries, but it is more challenging to implement and evaluate compared to extractive summarization. One of the most influential methods in abstractive summarization is the sequence-to-sequence CQ2-CQ model, which uses an encoder-decoder architecture. The encoder processes the input text and generates a hidden representation. The decoder uses this representation to generate the summary, word by word. In CQ2-CQ models, attention mechanisms are often used to allow the model to focus on different parts of the input text at each step of decoding. This is especially useful for handling long-range dependencies, such as understanding the context of a sentence in relation to others in the document. Recent advancements in summarization have been driven by transformer models, such as BERT and GPT. These models use the self-attention mechanism, which allows them to process the entire input sequence at once, making them more efficient than RNN-based models. BERT is typically used for extractive summarization, while GPT is more suited for abstractive summarization due to its ability to generate text. Transformers excel at handling long-range dependencies, meaning they can capture the context of words across long sequences, which is crucial for effective summarization. These models are often pre-trained on large corpora and then fine-tuned on summarization tasks, resulting in more accurate and fluent summaries. Evaluating the quality of a summary, especially for abstractive methods, is challenging. Some common evaluation metrics include ROUGE, Recall-Oriented Understudy for Gisting Evaluation. This is the most widely used metric for summarization, measuring the overlap of n-grams, words, or phrases between the generated summary and reference summaries. ROUGE provides recall, precision, and F1 scores, which help assess the quality of the summary. BLEU, Bilingual Evaluation Understudy Score. Though originally developed for machine translation, BLEU is also used to evaluate summarization by comparing n-grams in the output and reference summaries. Despite these automated metrics, human evaluation is often considered the gold standard in summarization tasks, especially when the goal is generating summaries that are fluent and meaningful. Text summarization has a wide range of applications across various domains. News summarization. Summarizing news articles enables users to quickly grasp the key points of an event without reading through long reports. Legal document summarization. Summarizing legal texts helps lawyers and researchers quickly understand case details, laws, and rulings. Research paper summarization. For researchers, summarization models can help them stay up to date with the latest research without reading entire papers. Chatbots and virtual assistants. Summarization techniques can be used to generate concise responses in conversational systems, improving user experience. Abstractive summarization, while powerful, faces several challenges. Generating summaries that are coherent and grammatically correct can be difficult, especially in long documents. Long-range dependencies between words and sentences often need to be preserved, which remains challenging. The models required for abstractive summarization are computationally expensive, particularly when training transformer models. Ensuring semantic accuracy while condensing information without losing important details is another ongoing challenge. Recent advancements have greatly improved the performance of summarization models. Pre-trained language models such as GPT-3, T5, and others have revolutionized abstractive summarization as they can generate human-like summaries with minimal fine-tuning. Fine-tuning these models on specific summarization tasks has led to significant improvements in accuracy and fluency. Multilingual summarization models are emerging, allowing for the generation of summaries in multiple languages from a single model. The development of more sophisticated evaluation metrics has also led to better assessment of model performance, helping in the continuous improvement of summarization systems. The future of text summarization looks promising with several exciting directions. Unsupervised methods. There is growing interest in developing summarization models that don't require large amounts of labeled data for training. Cross-lingual summarization. With globalization, the ability to summarize text in one language and produce summaries in other languages is becoming more important. Domain-specific summarization. Customizing summarization models to specific domains, e.g., medical, legal, could result in more relevant and context-aware summaries. Real-time summarization. There is a growing need for real-time summarization, especially for live events, such as news broadcasts or social media updates. In conclusion, text summarization is a critical task in NLP that allows us to efficiently process large volumes of text. While extractive summarization offers simplicity and coherence, abstractive summarization provides more fluent and concise outputs, though with greater challenges. The advent of transformer models like GPT and T5 has significantly improved the quality of abstractive summaries, making them closer to human-like outputs. As the field continues to evolve, we expect to see even more sophisticated models that can handle multilingual text, domain-specific contexts, and real-time summarization.